Now, judging by some of the questions which I saw a lot of you were confused about this particular thing. So I'll tell you one rule. Okay, one rule to always help you decide which is the anode, which is the cathode. Anode is where oxidation happens. So it is the half cell where oxidation happens, always. So wherever we see a loss of electrons happening at the particular electrode, we call that an anode. Okay, and cathode is where reduction happens. So wherever you see a gain of electrons happening, I call it the cathode. Clear? So this will clear your doubts about all this, wondering what to do, anode, cathode, all that confusion, right? So what's happening? So basically, electrons will flow from the negatively charged electrode zinc to the positively charged electrode copper, and current, you know, will obviously flow in the opposite direction. That's how it works. So what have we actually achieved here? With the help of a spontaneous redox reaction, we have been able to generate electrical energy. That's what a galvanic cell is all about. Okay. Now, Daniell cell obviously is going to be having a particular value, which is what brings us to the concept of electrode potential. Now that we know what is anode, now that we know what is cathode, and you know about all these charges which are happening, movement of these electrons which is happening, there has to be potential generated at the electrode. That is called the electrode potential. So basically it's a potential difference between what? Between the electrode and the electrolyte is called the electrode potential. There is electrode potential which is set up at each of the electrodes. If I subtract or add both these electrode potentials, I will arrive at the next thing, which is EMF. Electromotive force, also called as a cell potential. Don't worry, all of it we're going to go through. Okay. So let's have a look. So again, a recap. So due to oxidation occurring at zinc, it becomes a source of electrons. It acquires a negative charge. Okay. Due to reduction process occurring at the copper electrode, it acquires a positive charge and becomes a receiver of electrons. So that's what we understood so far, right? Okay. So that's basically it. So very, very important. Before we go into the actual concept of electrode potential, how do we represent a cell? Okay, so we know that one cell is made up of two half cells. Each half cell is got one electrode in it, either the anode or the cathode, immersed in a solution which serves like an electrolyte. Also, there is this very important thing called this salt bridge. Okay, so salt bridge, what is the job of a salt bridge? What is the saturated KCl? Now, salt bridges are usually glass tubes, okay, which basically contain some like a sort of a semi-solid paste. Okay, now what does it contain? It usually contains KCl. Sometimes it contains KNO3. It's basically something which is inert, okay, which doesn't really participate in the reaction. What is the job that it does? It is this salt which is actually captured in some semi-solid kind of a paste like agar. Now those of you who are bio students would know that agar is sort of like a jelly. It's basically obtained from a seaweed. So what do? You kind of put the KCl inside that and pack it tightly into this salt bridge. Now what does the salt bridge do? Now we learned that continuously what's been happening, zinc is undergoing oxidation. What is happening to copper? Copper is undergoing reduction. So there's going to be an accumulation of charges, right, between at each of the electrodes. So to kind of balance both, to maintain the electrical neutrality, to make sure that no accumulation of charges occurs at any one electrode, or in other words, to maintain electrical neutrality of the solution of the electrolyte, a salt bridge is used. That is the main function of a salt bridge. If I don't use a salt bridge, what is going to happen? Okay, one side is going to accumulate more charges than the other. Okay, and you're not going to have a proper distribution of charges. You're not going to be able to generate proper electrode potential, and you're not going to be having a proper value there. Okay, now when you see the definitions and the application of this electrode potential, you'll kind of understand why a salt bridge is so important. Okay, so how do we represent a cell? Coming back to that, always we will put the anode at the left hand side. We'll show these double lines, which is for the salt bridge, and then we put cathode in the right hand side. So how do I indicate each of the anode? I have to also mention the electrolytes in which it is dipped. So I will say in this it is zinc. So zinc, always mention the physical states, solid. Bar, ZnSO4, aqueous, because it is in a solution. Salt bridge. Copper sulfate, this should have been written aqueous. Bar, Cu. So anode, salt bridge, cathode. That's how it always works. Okay, so a better way to represent would be actually to indicate the ion which is involved. So zinc S bar Zn2 plus aqueous, salt bridge Cu2 plus aqueous bar Cu solid. That's how I would represent the Daniell cell. Okay, depending on whatever cell it is, you can represent it like this, because I told you how do you know the anode, what is an anode, what is a cathode. Based on oxidation happening at the anode, based on reduction happening at the cathode, you can get to know which one is the anode and which one is the cathode. Okay, so that will be pretty easy. Okay, so moving on to electrode potential. So electrode potential, as I told you, is basically this potential difference which is created between the electrode and the electrolyte. So the potential difference between both is what generates this electrode potential. Okay, so what is actually happening here? There's a flow of electrons which is happening. So that's what's creating this potential difference. Okay, now potential difference or electrode potential is usually given by E. Okay, now depending on in what form are we talking about? Are we talking about a tendency to undergo reduction, or are we talking about a tendency to undergo oxidation? It can have different subscripts. So if it's reduction, we say E red. If it is oxidation, we say E ox. Okay, so if I take a reaction like this, A2 plus adding electrons, what kind of reaction is it? Definitely reduction, because there's a gain. So the potential to do with that is E red. And if I have A undergoing oxidation losing electrons, then I would say E ox. So very, very important what is mentioned in this block, in this box here. E ox is equal to minus E red. So the electrode potential values, whether it is oxidation or whether it is reduction, is always going to be equal and opposite. In what? In sign. Very important. Okay, so the values will be the same, but the signs will be different. Okay, so I'll give you an example. Suppose I have mentioned okay, the E red for a particular reaction is 3.5 volts. That is the E red. So what do you think is going to be the E ox? Minus 3.5 volt. That's all there is to it, right? What is E red? Reduction potential, which is the tendency to gain electrons. What is E ox? Oxidation potential. What does it represent? The tendency to lose electrons. So clear? Are we learning something here? I'm sure all of you have learned okay, things which you are a little bit confused about. Moving on to standard reduction potential. Now that's just an extension of electrode potential. Now that you understood what is electrode potential, what is standard electrode potential? Now you always know that whenever you use the word standard in chemistry, it's talking about standard conditions, right? So that's basically what it is. So when do I record standard electrode potential? I will record it when the concentration of the ions in the solution is 1 molar or 1 mole per liter. If it's a gas, then I will say 1 atmosphere or 1 bar. And the temperature is taken to be room temperature, which is 298 Kelvin. Okay, so if I'm following these three conditions, standard conditions, I will put a not sign there. Not is for standard. So whenever we are mentioning standard conditions, we will mention a not. So E not is basically a standard reduction potential. Now, just to kind of maintain a proper flow, what is usually done is we just go by standard reduction potential. We don't deal with oxidation potentials. Okay. Now we just learned that it's basically the same thing except different in sign. Okay, when it comes to the value. So potential, of course, is mentioned in volts itself. So even electrode potential, even standard electrode potential at 298 Kelvin will be measured in terms of volts. So we will always assume it to be reduction electrode potential just for simplicity's sake. Now, at the beginning of the class, I had told you we're going to learn about the concept of electrode potential, and we're also going to learn about the importance of this electrochemical series. So we will be learning about electrochemical series as well, and then you will understand why I am mentioning it in terms of reduction electrode potential. Then it will make a lot more sense to you. Okay. So that's basically it. Now that you know what is electrode potential, a very, very important thing is cell potential or EMF, electromotive force. What is this electromotive force? Very simple. Now we are talking about electrode potential with respect to one electrode only, but we know there's two of them. So a cell can only work if there's two of them. Okay, can it work with one? It can't. So it has to work with two. So when I am finding the difference between the electrode potentials of the anode and the cathode, I will get the cell potential or the EMF. So what is it? It's basically E naught cell. So E naught cell is, pardon me for that. Okay. So E naught cell is basically, yeah. So E naught cell is basically the difference between the electrode potential of the cathode and the anode. Clear? Right? So we know what is the E naught now. We know that is the reduction potential of cathode and reduction potential of anode, right? When we subtract them, we get it as the E naught of the cell. What is E naught of the cell? Cell potential or EMF. Absolutely clear, right? Okay, I hope you're really enjoying this, and all of you who are very, very confused. I notice a lot of you were very, very confused based on the questions which I received, that all of this makes a lot more sense now, right? So that was the point of the webinar, to make all these concepts a lot more simple. And of course, if you're going to continue with these classes, these master classes of mine, this will be my style of teaching. So whatever I'm going to teach you, physical chemistry, inorganic, organic, you name it, it's going to be like this, so that you always, of course, understand the topics very well. I will also leave a lot of application based questions for you, just to kind of understand it, the concept as far as your syllabus is concerned, your competitive exams are concerned, but also just out of interest. Okay, how do you apply a concept? What's the whole point of learning these things? So we will look at it in that way. Okay, so in the most interesting way possible, because I always believe that if something is made interesting, you will learn it better and you will score better, right? So rather than something which is made very boring, then you will be, something which is unnecessarily made boring sometimes, right? So it all depends upon, every single topic in the universe can be made interesting. So it just depends on the way it's put forward, right? So this is another formula. In some books, they will probably give it to you as right, E naught right, and they may say E naught left. Okay, so we know that based on the cell representation, the left side electrode is the anode and the right side electrode is the cathode. So that's what we basically mean by right and left here. So if you see right and left also, it's basically the same thing, but I would prefer if you use it as cathode and anode, because it's just more technical, right? Okay, so we will try to look at questions on this also. We will look at this a little later. Okay, so questions on this also we will look at, and we'll take a sort of break after this, because we've been talking quite a lot about chemistry. So we'll try to take a break from this. Okay, so we will come back to this from this slide onward. Okay, so I hope that all of you have understood this concept. So first, let's check. Have you understood this, right? Okay. Okay, so are all the concepts clear? Yes, so yes, that's wonderful. Okay, nice. Yes, okay. If any of you are finding it a little bit hard, or thinking this is just not relevant for me, I'm in 11th grade, yes, this topic was chosen in a way for both of you based on a greater percentage of 12th graders. So it's a 12th standard topic which is there, but definitely 11th graders are going to go into 12th. So of course, it's important for everybody. Okay, so it is something which you learn, and of course, in your master classes for 11th grade alone, we will deal with your topics in your syllabus. Don't worry, I'm not going to be talking about electrode potential from day one. I will be dealing with whatever topics has to be taught for you. So don't worry about it going over your head, or thinking, why should I learn about electrode potential in 11th grade? It's just a topic which is there, and all of you who are attending, just keep an open mind, and if you're learning something new, good. So you learned something new today, right? That was the point. Okay, fine. So we'll kind of take a break from all these topics which we are dealing with today, and just let's find out something about you. Okay, so what we're going to do now is, I'm going to, okay, I'll close the poll now. Okay. Yeah, so I'm going to just share another poll with you. This is to do with what career choices you people are making. Okay, now obviously all of you must be thinking of the careers which you want to pick, and you're already very excited about how the exams you're going to write, everything that you're going to study and all that. So let's just find out what are the careers. So I've chosen some of the random ones which I personally found in my students was very common. Okay, so let's see. In case it's not there in the options, you can always pick others. Okay. Yeah, so let's see. Okay. I will tell you the poll response also. I'm sure you must be curious to find out. Okay. Okay, so it looks like there's around almost close to 50% of you for engineering, 29% of you medicine, 2% architecture, 9% pure sciences, and 9% others. So, okay, so I'm interested to know what are the ones in others, but anyway, it always doesn't surprise me that the number one is always engineering. So 51% of you is actually engineering. So that's always the case in every single class of which I've taken, I think, so far. And I've dealt with thousands of students. Okay, so 1,000+ students, and maybe 5 years that I've taught, but I've dealt with a lot of you. So I've always noticed the one common question which I ask in the class, and I always notice is engineering, 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 which is the highest. Okay, fine. Pure sciences is 10%, not bad. So there's people like me there who actually want to go into pure chemistry or pure physics or whatever it is you're interested in to do with science. Okay, fantastic. So let's close. Right. So let's continue now. Okay, so yeah. So we were talking about the concept of cell potential, right? So let's look at the cell potential here. So we're looking at A, B, and C. All of them are in terms of reduction. So you notice the values. So you notice how they're only different in sign. So if I'm going to calculate the cell potential, I will look at it in terms of 3.5 volt plus or 3.5 negative, depending on whether I'm seeing it in terms of reduction or oxidation. So as I told you, for simplicity's sake, always it's given in terms of reduction. If it is specifically asked you in terms of oxidation, just change the sign. That's all you have to do. Okay. Fine. So the EMF of the Daniel cell, which we spoke about, actually works out to be around 1.1 volt. Okay. Yes. Moving on to our next concept. Okay. Now we will do some questions if we have time for it. On the concept of electrode potential as well. But before that, let's try to do electrochemical series as well. I don't doubt if we will have time for Nernst equation, but we will see if electrochemical series we can cover that as well. Okay, so what is this electrochemical series? Okay, now electrochemical series is a series of what we call as redox couples. Redox couples are just another way of calling half cells. So we are talking about the arrangement of these different half cells, their electrode potential values in terms of reduction potential. So all the values which you see here, 2.81 volt, minus 3.05 volt, all are in terms of their standard reduction potential values. Okay, so at 298 Kelvin. So you see a couple of stuff here. Now this is just a very condensed version of the actual series. The actual series, of course, is a lot longer, bigger. So you see fluorine kind of heading the list there, and you see lithium at the bottom of the list. So what does that tell you? And very importantly, you see this thing marked in red of hydrogen. So it shows H plus plus electron giving you hydrogen. So what is this? This is corresponding to an electrode which is called the SHE, She. Okay, so it stands for standard hydrogen electrode, which is what we call as a reference electrode. Okay, so it is a reference electrode. So like I said, you can never calculate the cell potential of a cell by itself. Just one half cell you cannot. Connect it with something, right? So what we are connected with? I connected it with an electrode, which is called a reference electrode. Now, a reference electrode is something whose electrode potential is been kept or balanced to 0 volt. So that is kept as my reference. So with reference to this electrode, I can calculate the standard electrode potential of the electrode of copper or zinc or whatever I wish to calculate. Got it? That's why it's called reference. Okay. So we'll take a look at what is the construction of it later. But now let's try to understand this electrochemical series. Very, very important to understand this. Okay. So you see fluorine right at the top. So have you noticing a pattern here? So everything which is above a standard hydrogen electrode, which is maintained at 0 volt, the positive values And then you see negative values below it. The positive value. So what is at the top over here? You see the one with the highest electrode potential here being fluorine. Okay, so what does that mean? It means fluorine has the greatest tendency to undergo reduction. In other words, it is the strongest oxidizing agent. Is that clear? Okay, so that's the greatest tendency to undergo reduction. What about lithium here? So lithium here is minus 3.05 volt, pretty negative. So it is the weakest oxidizing agent. Not only that, it is the strongest reducing agent. Why? Because it has got the greatest tendency to lose electrons. Though you have everything in terms of reduction, we do know when we have a certain understanding of the periodic table. Okay, what is something funny about these two, fluorine and lithium, with response to the periodic table, right? Lithium is an alkali metal, so it comes right at group 1. So it comes at the far left of your periodic table. Fluorine is group 17. It's a halogen. It comes right at the other end of the periodic table, right? So we know that electronegativity is something which is increasing from left to right across the period in a periodic table. So lithium is a very, very electropositive metal. What is electropositive? The tendency to lose electrons of lithium is extremely high. Whereas fluorine has a very great tendency to accept electrons because it's a halogen. Halogens we know are just one electron short of their octet. So they desperately want to avoid electrons being lost. So fluorine is electropositive and it tells a lot of information to us, right? Okay. So this is just the list now. This is just somewhat a little bigger list which was there in your text, which I just cut up and put. Okay. So don't think it's such a small list. It's even more bigger than this. It's just a small little bit of it is put for you. Okay. So why I put this is because in relation to the problem which I've kept for you to do. Okay. Now we'll try to do this problem and then we'll see if there's any questions on any of the topics discussed, because we have almost 15 minutes left, little less than 15 minutes. Let's try this. Okay. So these are the things which we're going to try based on everything we have learned. So we have learned about the two concepts which were supposed to be very important for you to grasp, get a hold on. So let's see this. So for this redox reaction, write out the oxidation and reduction half reactions. Create a cell diagram to match your equation. So this is the reaction given. So obviously you find tin or SN undergoing oxidation, and you find PB undergoing reduction, right? So which is the anode? The anode has to be written on the left hand side. So we put a Sol bridge here. Anode has to be written in the left hand side. So we will write tin bar SN2 plus aqueous, PB 2 plus aqueous, bar PBS. This would be your cell diagram. So when I say cell diagram, you basically mean it's a cell representation diagram. Okay. If you want to write the oxidation and reduction half reactions, now some of you are asking me in the questions which I already saw, what is this N value? When they say Ne, what does it mean? It's the number of electrons. How do I know number of electrons? That is based on the charges which you see. So if you're seeing PB2 plus, SN2 plus, you have to get the idea that it is 2 electrons we're talking about. If you saw one charge, it's 1 electron, as simple as that. Okay. So I will just write SN becoming SN2 plus 2 electrons. That would be my oxidation half cell. And PB2 plus is adding 2 electrons, giving PB. That would be my reduction equation. Clear? So that's how we get all this. I hope all of this is absolutely clear. Okay. Let's look at the next question. If copper 2 plus ions in solution around a copper metal electrode is the cathode of a cell, and K plus ions in solution around a K metal or potassium metal electrode is the anode of a cell, which half cell has a higher potential to be reduced? higher potential to be, so higher reduction potential, which has higher. Okay, so let's look at the electrochemical series, which will kind of help you. So where's copper? Copper is here. Okay, where's potassium? Potassium is here. So potassium is very negative. Why? Alkali metal, group 1. It has a very negative electrode potential. Copper is much higher. Okay, it's right here. It's reference to 0. It has actually got positive value. So 0.52 volt. Okay, sorry, this one, sorry, 0.34 volt, which is copper 2 plus ion, right? So this is the one, sorry. I didn't see the positive there. Yeah, so this was the one. 0.34 and minus 2.93. So which one has a higher reduction potential? Obviously, which one is it? Copper, right? So you will know that. Now, in case you didn't have the electrochemical series in front of you and you have asked this question, obviously, we're not going to give you this electrochemical series. Please don't try to memorize this series. Try to kind of see the logic. When you look at potassium and look at copper, now copper is a D block element. Potassium is a alkali metal. So when you know about your periodic table pretty well, which you should be in 12th grade because you've learned quite a lot about it in 11th, and 11th graders also, you will be learning a lot about periodic table in this year. So don't worry, you will totally know about all these elements. You will kind of get the idea. So which one is more electropositive? So electropositive means tendency to undergo oxidation is higher, meaning it will have a negative reduction potential. Copper. So in connection with this, definitely copper is the one. Higher potential to be reduced, meaning a more positive value compared to potassium. What type of a reaction provides the basis for a cell potential? So what type of a reaction? Obviously it is redox. We know that, right? How is the cell potential measured and with what device is it measured? Of course, it is in volts by a voltmeter. Okay, so voltmeter, right? So these are all the answers. So very simple questions just based on this. Of course, if you're going to have a class only for 11th grade on electrochemistry, we will be going a little faster. We will try to cover more and more concepts which we can in the class. Same time, trying to simplify things, because this is my manner of teaching, always simplify everything as much as possible. We will have a lot more time as well because your session will be mostly 1.5 to 1 hour 45 minutes long. So we'll have a lot of time to do plenty of concepts, lot of application, enough time for questions and all of that. So don't worry at all. It will strictly be based on your syllabus as well, and we'll try to apply it to the maximum. Okay, so this is the class which is for both of you. So I've tried to approach it in a slightly simpler version way than I normally would had it only been 12th graders. Okay. So this is the standard hydrogen electrode for those of you who wanted to see what it looks like. So it's basically a hydrogen electrode, which is basically a platinum electrode. Okay, a platinum electrode which is covered with what we call as platinum black. It's called platinized platinum. It's basically just a powdered platinum applied on the platinum so that it increases the surface area and makes it a better, catalyst. So you'll learn a lot about that in surface chemistry, the chapter which you have. Immersed in a solution of an acid. Okay, it's usually 1 molar HCl which is taken, and then you also have hydrogen gas which is constantly bubbled. So you will have the reaction of this happening. So H plus ions from the medium undergoing reduction and forming hydrogen gas. So how will you represent it? You will represent it alone like this. PT, platinum solid, bar H2 gas, bar H plus aqueous coming from the aqueous medium in which it is immersed. So this is basically how you'd represent a standard hydrogen electrode. Now don't get the picture that standard hydrogen electrodes are the only reference electrode available. There's plenty available. In fact, this is quite a painful one to use in the sense that it's very difficult because I need to maintain the hydrogen gas at 1 bar. 1 molar HCl is fine, I can achieve that. But this hydrogen gas at 1 bar, and platinum is basically expensive, right? It's an expensive thing. So practically when you're looking at using SHE, you would prefer not to use it. So there are a lot of other reference electrodes which you can choose from, which are even more better, easier to use with. I'll just give you one example. One of it is what we call as a standard calomel electrode. That's a very popular reference electrode which is used. SCE. Okay, so that's basically it. Okay. So yeah, so we can try to calculate the E0 cell for this. Now before we go into this, this is basically utilizing the formulas which we learned in this class. Okay, are there any questions which you have since we have very less time? Any questions? Okay. Yes. Can you please tell me how can I prepare for chemistry IIT? Can I know about batteries? Okay, there's no time to talk about batteries today, unfortunately. Uh, okay. Okay, I guess whatever I see oxidation, uh, how can we know it's anode and cathode? Uh, can we store copper sulfate solution in a zinc pot? Okay, that's a nice question. Okay, so can we store copper sulfate in a zinc pot? One of you have asked this. Okay, now, yes. So the answer to that is no. We cannot. Okay, why? Because what will happen is zinc will actually react with the copper sulfate, okay, displace it out of the solution and form zinc sulfate and copper. So this is basically copper will get deposited. So if you're going to have copper sulfate in a zinc pot, the zinc will no longer remain as zinc. It will become copper. So definitely you can't, because zinc is the more reactive of the two metals. When I see zinc and copper, zinc is the more reactive one. So basically what is happening here is copper sulfate has become copper. So what has happened to copper there? Copper has basically undergone reduction. Okay, so that is the answer to your question. I hope you're happy with it. Okay. How does salt bridge balance the electrons? Salt bridge basically helps to balance the electrons by neutralizing the charges which are excess. So whatever charges are excess in a particular half cell, that will be neutralized by the ions in the salt bridge. So suppose I have KCl in the salt bridge, then K plus and Cl minus will be the ions which are there. So the K plus is going to come and neutralize the sulfate ions if sulfate ions are in excess in the electrolyte. That's how it works. So basically neutralizes the excess charge, and that's how it creates the electrical neutrality. Okay, interesting class. Nice to see that. I want to know about Nernst equation. Yes, unfortunately, I don't have time to teach you that, right? Okay, fully confident. Somebody is telling, very good. Okay, quite happy. Questions, numerical problems, solve bridge. Aneet, you said something about your college life. Okay, somebody is okay. What about my college life? Okay, see, there'll be time to discuss all of this later on, not in this webinar. Okay, so great. Okay, can I get a recording? Yes, you definitely can get a recording of this. Definitely. What medical books should I don't have Solbridge. What happens? I think you have understood that. Can I have your number? Okay, wonderful class. Okay, great. So very, very nice to know. I hope I've answered all your questions. Okay, your batch has been absolutely wonderful. Okay, keep it up. Those of you who have attended this webinar. Very interactive. It's been a pleasure to teach all of you. I hope all of you had a really great time and you've understood a lot of the concepts. So if you're going to continue these classes with me, you will understand all the concepts. Everything will be simplified for you to the maximum. And I wish you all the very best for your life and everything that you're going to do. I'm sure that you will pursue everything with full vigor, okay, and passion, and work hard.